Hello, Quantitative Methods class. Today we're going to talk about the simplest of all inferential statistics, the one-sample z-test. We learned a lot about the logic and the process of null hypothesis significance testing, but let's see it in action. Let's see it with this very, very simple situation, the one-sample z-test. So what we're going to talk about today, we're going to talk about one-sample z-test, and then we're going to go and talk about some of the assumptions that underlie many of the inferential statistics that we use with null hypothesis significance testing. All right. The first thing that I want to mention is, when are we going to use the one-sample z-test? I promise you, one of the biggest skills of this class is not necessarily knowing how to conduct these statistics. You're not going to do them by hand very frequently. But what you will have to know is under what circumstances do you need to use this statistic or this other statistic. So this is something that is very, very important for us to understand. So we're going to start very simple here. This is going to be a flow chart for pretty much all of the statistics that we're going to talk about before test 2. For all of these statistics, we're going to be comparing two means. So the answer to this question, are we comparing two means, trying to see if in the population there are population mean differences, we're going to use these categories of statistics. So are we comparing two means? Yes. Okay. Here's the next question that we have to ask ourselves. Are we comparing a sample mean to a population mean? Or is it the case that we're just comparing two sample means? So let me give you some examples here. Suppose, if you would, that we are trying to figure out, do people that own a dog have less anxiety or a different level of anxiety than everybody else? So we might be comparing maybe 20 randomly selected people that own a dog, measure them on anxiety, and then compare that to the population mean of a test of anxiety. If that's the case, we are going to move up in this flow chart. Yes, we're comparing a sample to a population. Maybe it's the case that we're comparing two sample means. So let's say that we have a drug study, and we have an experimental group that has the drug and a control group that takes the placebo. And we don't care about, are those sample means different? Because no duh, if we can just look at them and see that they're different. We care about inferring from these sample means to the population means, okay? If we were to give this drug to everybody, would there be a difference between the placebo and the experimental drug? So in that situation, we have two samples. Now I have to mention that it's very rare or somewhat weird that we're comparing a sample mean to a population mean. In many situations in psychology, we don't have the population mean. We don't have the population variance. Why? Because many times in psychology, we are creating a new task. And how do we know what the population mean or variance of a task is? Because we have to give that out to a ton of people. So we don't have the resources to do that. We don't have the time to do that. And many times we're creating new tests or modifying some tests. So very rarely is it the case that we have access to a population mean or a population variance. So that means that these tests that we're going to be looking at right now are not as useful as some of the other tests, but they're still important for us to learn about. One of those reasons is because they're very simple. Every other test that we're going to talk about before test 2 is a modification of the one-sample z-test. So we're going to start off simple and impractical, because we don't really have the population mean most of the time, and then we're going to move to tests that are more practical, but a little bit more complicated. Okay, so are we comparing a sample to a population? Yes. Let's say that that's the case. The next question that we have to ask is, do we have the population variance? If we do have the population variance, we know the population mean and the population variance, maybe for my example for dogs and anxiety, we know with a measure of anxiety what the true population mean of that test is and what the true population variance is. We can use a one-sample z-test. So if we've got the population variance here as denoted by sigma squared. Remember, sigma is the parameter, which refers to a characteristic of the population. If we don't have the population variance, we use a test called the one sample t-test. What's the difference between a z and a t? Hold that question, we're going to get to it here in a couple of modules. Okay, so if we've got comparing a sample to a population, we're either doing a one sample z-test or one sample t-test, depending on if we have access to what the true population variance is. So let's say that we're comparing two sample means, something that happens much more frequently. All right, the next question that we have to ask ourselves is, how do we manipulate the independent variable? Did we manipulate it between subjects, or did we manipulate it within subjects? So in the very first module, I told you that this was an important distinction, and I hope you took that to heart and that you understand the difference between a between subjects and a within subjects manipulation, because it's going to appear here, it's going to appear many more times before this class is done. All right, what kind of experimental manipulation we use dictates the kind of statistic that we're going to do. So if we used a between subjects or between groups manipulation, we do a test called the independent samples t-test. All right, focus here on independent. Independent, you are in this group or you're in that group. Okay, these groups are independent of one another. It's not like somebody's in this condition and this condition. They are completely separate from one another, and our comparison is between these two groups. So between the groups, between subjects, these groups are independent of one another, independent samples t-test. All right. If we have a within subjects manipulation, we do a statistic called the paired samples t-test. All right, paired samples t-test. Sometimes this is called dependent samples t-test to contrast it with the independent samples t-test. Sometimes this is called the repeated measures t-test because you are measuring the dependent variable multiple times if you have a within subjects design. Remember, for the within subjects design, within subjects manipulation, we have subjects are in both the experimental and the control condition. If it's at two levels, could be at many different levels. Maybe we're doing a longitudinal type design and we're measuring you at age 10, 20, 30, 40, 50. It's still a within subjects design. We are measuring the same person over a long period of time. Paired here, because all data points for a within subjects designed where we have two levels have two data points, the data under the experimental condition, the data under the control condition, and they're paired because the same subject contributed data both under the experimental condition and the control condition. That's why they're paired in a certain way. We're going to make use of that when we conduct our statistic. Why did I spend so much time on this? It's a very important skill for you to have to know which kind of statistical test we need to use for whichever problem that we do in research. It's very easy to click in SPSS, hey, I want to do an independent samples t-test. It's more difficult to figure out when we need to do an independent samples t-test. So I want you to be mindful of this and definitely memorize this flowchart or a flowchart similar to this. This flowchart will get more complicated as the experimental designs get more complicated before test 3 and after test 3. Okay. How do we do our inferential statistics? Well, the textbook says that there's that there's 6 steps to do this. If you talk with the other psychology professors that teach this class, they might have a different number of steps as well. But I was told that there are 4 steps to doing this process, and that's how I'm going to teach you guys how to do this. What we're actually doing doesn't change if you were looking at how I do it compared to how Chuck does it, compared to how Brian does it, compared to how the book does it. They're all exactly the same. It's just what you call step 4 and what you call step 3 might vary a little bit. So what I call step 2, for instance, the book breaks up into 2 separate steps. What I call step 3, they break off into 2 separate steps as well. It's, you know, all the same thing, just how you conceptualize it. So this is what we're going to do. First step of null hypothesis significance testing. We're going to state what the null and the alternative hypotheses are. what are these? We're going to write them out in mathematical notation. Step 2, we are going to determine the decision criteria. When are we going to reject the null hypothesis and when we're going to retain the null hypothesis? In here, we're going to list all of the information that will help us make that decision. It's all of the decision information about when we reject and when we retain. I'd also like you to include what kind of test we're doing in this step as well. Step 3, this is where the math actually comes into play. Notice that for this process, no math here, no math here. Only in step 3 do we get the actual math. I've mentioned this before, but the difficulty in this class is not really the math. In fact, that most of the time brings people's grades up. The math is fairly simple. All right, it's just at the level of algebra. At most algebra, okay? It doesn't go into calculus or anything like that. But the concepts are what's difficult in this class. Understanding why we do the things that we do, understanding when to do certain things. That is the important aspect of this class. So many people might think that step 3 is the hardest part of this entire process of doing inferential statistics. And it might be the most time consuming, but by far the part that you're probably going to have the most difficulties with is step 4. Okay, this is where we write out our conclusion of our statistical test. Okay, do we reject or do we retain the null hypothesis? And then we'll write it up as if we were to write it in APA style paper. This is the step that some of you will struggle with. If you've taken elementary statistics before over with the math department, since they are not tied to a particular discipline, they're teaching you statistics for all disciplines, they don't go very much in detail about this step, and you might have learned something like you put reject or you put fail to reject, and that's all you need to do to write up your conclusion. And that is kind of true, but we're not going to do that in this class. We're going to be a lot more thorough to really understand what's going on. If you just write the word reject, you're not doing this step correctly, and you might not be understanding exactly what's going on here. So this step is going to be a lot more involved than it has been in the past for many of you. Okay, so let's do the most basic inferential statistic that we can conduct, the one sample z-test. This is where we are comparing a sample mean to a population mean. And we know what one of the population means is, and we've got one sample. So we're trying to look at that sample and try to figure out what that sample says about its population mean, and trying to see if these two population means are similar or different from one another. All right, that is what we're doing with a one sample z-test. This is where we have the population mean and we have the population variance. All right, we're going to use the z-distribution. All right, remember that standard normal distribution, the table that I gave you a little while ago. That is the distribution that we're going to use to answer some questions about this, more about this later. But that's why it's called a z-test, because we're using the z-distribution. Here's the first test problem that we're going to look at here. And you can tell that I was angry at Mac users when I was writing up this question. Do Mac users have a different level of creativity than the average American? All right, we conduct a study and randomly select 25 Mac users from the general population. They have an average of 15 on the creativity test and a standard deviation of 5. The national average for this creativity test is 20 and the variance is 36. Do Mac users have a different, and I bolded that because it's going to be important a little bit later, population mean creativity score than the national average? Okay, so first and foremost, why is this problem? Why do we need a one sample z-test? Okay, so we've got a sample mean, okay, a 15 for the Mac users. Okay, we're sampling all Mac users, and we're comparing it to a national average. So something that supposedly has the true population mean, and we have the true population variance. So what are we going to do? We're going to do a one sample z-test. All right. One thing that I would suggest you to do for all of these problems, you don't have to do this, but I would strongly, strongly recommend it, is to look at the problem and write down all the information that you have from the problem. All right, so the first thing that I'm going to look at is see where I see a number and then think about what that number is. First number I get to is 25 Mac users. What is this? Well, this is my sample size. Okay, this is the sample of Mac users that, this number of Mac users that we sampled from the general population of all Mac users. So this is our sample size, and we refer to that as N. So I'm going to write down N and say that my N is 25. All right, let's go to the next number that we have here. They have an average of 15 on the creativity test. So this is a mean, but more importantly, it's a sample mean, okay? It's not a population mean because I'm taking the average of these 25 as opposed to all Mac users. What I like to do, because most of the time we're dealing with multiple means and multiple standard deviations and variances, I give a little indication as to what mean this is referring to, a subscript. So I'm going to write down M Mac or X bar Mac, okay? M or X bar, both of these are ways that we refer to a sample mean. And the Mac here, I have written just to let me know that it's the sample mean of the Mac users, all right? Is equal to, not 25. Let me fix that real quick. All right, there we go, much better. Don't you love it when you find things that you've made a mistake in when as you're doing the lecture? Lovely. Okay, so we've got our sample means here. Again, I use my subscript to denote which particular sample mean I'm referring to. Standard deviation of 5, well, that is a standard deviation, and more importantly, it is a sample standard deviation. So I either abbreviate this SD or with a lowercase s, and I'll give it a subscript, Mac, okay, equals 5. The national average, well, national average is a population mean, so I'm going to use mu, is 20. So I have mu, and to refer to what particular population mean, I have my subscript of nation. It could be nation, it could be national, it could be USA. Doesn't really matter as long as I know what's going on here. Equals 20, and I have the population variance. For population variance, it's sigma squared, and I can easily calculate what the population standard deviation is, so I just went ahead and did that. I could do the same thing here with my sample standard deviation and give myself the sample variance if that were important for this question. Turns out it's not, but I could have done that as well. Okay, so I've written out all of the numeric information, and this is going to be very helpful for me when I'm doing this problem. One last bit, do Mac users have a different population mean creativity test score than the national average? Okay. When I'm looking at a word like different, it lets me know whether or not I have a directional hypothesis. Do I have a prediction about whether or not the Mac users have a higher population mean than everybody else, a lower population mean than everybody else, or just if there's a difference? This is important when we set up our critical values, okay, our cutoff values for when we reject and when we retain the null hypothesis. Let me do a little bit of drawing right here. All right, so we have our lovely standard normal distribution. You can easily tell that that's what this thing is. We need to set up a rejection region of when we have a finding that's going to be so extreme that we reject the null hypothesis. Now, if it's different, if we're just looking for a difference, we need two cutoff values. We need two rejection regions. A rejection region that's to the left side of our distribution, and a rejection region that's to the right side of our distribution. All right. Another way of referring to this kind of test would be a two-tailed test. Two-tailed because we have a rejection region on the left and right side of our distribution, okay? It's at two different tails. If, on the other hand, I had said, do Mac users have a higher population mean creativity score than the national average? Okay, I would only have one rejection region, okay? Only on one side of the distribution, and if it's higher, it's going to be on the right side. Now, this rejection rate is only one tail, so we would call this a one-tailed test. One-tailed test, we have a directional hypothesis. We have a hypothesis about whether the mean difference is going to be larger or smaller than the other one. All right. But if we just say different, we have a two-tailed test. Okay, we don't have a directional hypothesis. Okay, let's go about our business and state the hypotheses. Okay, so we have our null hypothesis and we have our alternative hypothesis. And let me start off by writing them out. Okay, the way that I'm going to refer to my alternative hypothesis is H sub A. Okay, that's how I refer to my alternative hypothesis. My null hypothesis is going to be H sub 0. And this part I typically make a Mortal Kombat reference because there's a character named Sub-Zero. But as the years have gone on, you guys have no idea about Mortal Kombat, so I'll just keep that reference to myself. But you can Google Sub-Zero if you want to. All right. So what is our alternative hypothesis and what is our null hypothesis? Well, our alternative hypothesis we actually see at the very end of that problem, okay? We're trying to test if Mac users have a different population mean creativity score than the national average. The way that I am going to write is different than in mathematical notation is I'm going to use the does not equal sign. Okay, this means it's different than. All right, and I'm comparing two different means and I'm trying to see if they're different to one another. All right, one of the means that I'm comparing to is the population mean for everybody. Okay, so this is one of the ones that I'm trying to see if it's different than. What do I write over here? Now you might be tempted to write the sample mean. All right, the sample mean of Mac users, but that's not ultimately what we're trying to test. We can see with our eyes that the sample mean is different than the population mean. The sample mean is 15. The population mean is 20. We don't need any fancy statistics to tell us that that's different. But ultimately, we don't care about sample means. All right, we do not care about them whatsoever. We care about what the sample means tell us about the population means. So what we're going to write here is another mu, because we care about the population mean, but that of the Mac users, okay? Not the most beautiful Mac, but it will suffice, okay? So the mu, the population mean of creativity for Mac users is not equal to the population mean of everybody in the nation. Okay, that's our alternative hypothesis. Our null hypothesis is always the exact opposite of the alternative. So instead of does not equal, our null hypothesis is going to be equal. So the mu of the nation, the population mean of everybody in the nation, their creativity scores, is equal to the population mean of Mac users. All right. The null hypothesis, of course, states that there's no effect, okay, no difference between the population mean of Mac users and the entire nation. The alternative states that there isn't a difference. There is an effect in some way. Here's a hint to help you on how you write these null hypotheses and alternatives. For the null, there's always going to be an equal sign in the null hypothesis somewhere. It's either going to be an equal sign like this. It's going to be a less than or equal to, or a greater than or equal to. But this equals part is always the same and always going to be here for the null hypothesis. For the alternative, however, there is never going to be that equal sign. So we're going to have does not equal, less than, or greater than. Okay, these appear in the alternative hypothesis. These appear in the null hypothesis. Okay, makes sense? All right, so I did that piecemeal because I could just show you. There we go. This is exactly what we have already written. All right, here. The population mean of MAC users is equal to the population mean of the nation for the null hypothesis, and the population mean of MAC users is not equal to the population mean and creativity score of the nation in our alternative hypothesis. But this is only one way that we can write it up. I think it's the most easy way to understand what's going on, but we could just as easily write the null and alternative these other ways as well. Since we know what the population mean of the nation is, I could have just substituted 20. Okay, the population mean of MAC users minus 20 should be equal to 0 under the null hypothesis. So any of these ways are sufficient in writing out the null hypothesis, and you might see them in different textbooks, in different classes, but they all pretty much are identical. Statisticians are notorious about using different notations. Okay, one statistician will use X bar, another one will use M, and for the student it gets very confusing. Okay, as when I read professional statistics papers, oh man, they will use all kinds of different notations and it's never the same, and it's very, very frustrating. I wish they would all get together and come up with a consistent way of doing that, but unfortunately they have not. So that's one of the reasons that I show you all of these different ways to do them and show you that they're equivalent. I know that you're probably thinking, I just want one way to do it, but you're not going to see just one way to do it. All right. So step 2, what is our decision criterion? Okay, what are our decision criteria? How do we make a decision about whether or not we reject the null hypothesis or we retain the null hypothesis? Well, one thing that I want to remind you guys about is that whenever we do null hypothesis significance testing, whenever we do inferential statistics, there is always a probability that we make a mistake. All right, we are never 100% sure of our statistical conclusion. All right, it can always be the case that we are mistaken. It can always be the case that we find this difference, we say that there's an effect, but we found that difference just due to random chance. Suppose we are conducting a study to try to see if UNG students and UGA students are equivalent on psychology test scores. And we see that UNG students scored an average of 100 on a psychology test and UGA scored an average of 50 on that psychology test. I could have just found that major difference just due to chance. Now, mind you, it's probably very, very small, but there is some likelihood that I end up making that mistake. So there has to be some probability that we're comfortable with in making a mistake, or otherwise we're never going to reject the null hypothesis. And the criterion that psychologists use, that Fisher said randomly one time, hey, why don't we go with the cutoff point of 0.05, and that's the one that we've used ever since. Okay, and very rarely does it deviate from this. All right, let me talk a little bit about what this means here. There's 2 types of errors that we can make in null hypothesis significance testing, a type 1 error or a type 2 error. Type 1 error is when the null hypothesis is indeed true, and it's the error that we reject the null hypothesis. We say that there's an effect, when in actuality there is absolutely no effect. Another way of describing this is a false positive. All right, we're saying something's there, but it's really not there. Think about if you went and got a coronavirus test. You get the coronavirus test and they say, oh no, you've got coronavirus, but you actually do not. That would be a false positive, and that's equivalent to a type 1 error. All right, so what we have decided in psychology is that we are going to set up our decision-making process by setting our type 1 error rate, the probability that we make a type 1 error, to a 5% chance. Okay, that's the percentage, the proportion's 0.05. Okay, there's always, if the null hypothesis is true in psychology, there is a 5% chance that we reject the null hypothesis and say that there is truly an effect, when in actuality there is not. We know what the data would look like under the null hypothesis, and that's why we're able to set the type 1 error rate. Okay, we know what the data would look like if there's no effect between these 2 different population means. All right, So another name for our type 1 error rate is alpha. Just to remind you, the other type of error that we can make is a type 2 error. This is when the alternative hypothesis is actually true. All right, there is actually a difference. And yet we say, hey, we think that the null does a pretty good job of accounting for this. So this is where we fail to reject the null hypothesis when the null hypothesis is actually false. A good way of saying this is a miss. In our coronavirus situation, this is where we say, hey, you don't have the coronavirus, but in actuality, you do. So it's a miss. Now, in psychology and in statistics in general, I just shouldn't say psychology, we never know the magnitude of the difference. Is it going to be a small difference between Mac users and the national average? Is it going to be a moderately sized difference? Is it going to be a large difference? If we knew this, okay, if we knew this, we could set our type 2 error rate. And another way of abbreviating type 2 error rate is beta. But we don't know the magnitude of the difference. That's why we're conducting the research in the first place. So we can't set our type 2 error rate before the study begins. We would have to know the true population mean difference to set our type 2 error rate. And in that way, we don't know what our type 2 error rate is when we're conducting studies. Okay, so that's why we set the type 1 error rate. We don't set the type 2 error rate. Okay, so a lot of information there, but it's important nonetheless. All right, what kind of test are we doing? We've already mentioned we're doing a one sample z-test because we're comparing a sample mean to a population mean. We have the population variance. It is one sample z-test time. Okay, what kind of test are we doing? Are we doing a one-tailed test or a two-tailed test? Well, it turns out we're doing a two-tailed test. So what is our criterion? So when are we going to reject the null hypothesis, and when are we going to retain the null hypothesis? Well, this requires a little bit of thought. So if we have the sample mean, if we have the population mean, if we have the sample size, if we have the population variance, you know what we can do with that? We can draw exactly what the sampling distribution would look like, okay? What the sampling distribution would look like under the null hypothesis, okay? If we were drawing from the population, just a sample, okay? We know, all right, what the mean is going to be, okay? Because the mean is equal to the population mean for the sampling distribution, okay? If our number of subjects is 30 or greater, we know that the shape is going to be normal, okay? We also know, okay, what is the variability of this sampling distribution, okay? Because remember, the standard deviation of a sampling distribution is equal to what the population standard deviation is over the square root of n, the number of subjects that we're sampling. And this has a special name, if you guys could remember. This is the standard error of the mean, okay? Sometimes called standard error, sometimes called SE. So we know exactly what this sampling distribution is going to look like. But we have a problem, okay? This value, okay, this value right here, okay, where we get only a certain percentage of time, this is going to be different with every single distribution we have. Okay, it's going to be different if our population mean is 500, it's going to be different if it's 300 or 30, it's going to differ with the number of subjects that we have and what the true population standard deviation is. But we could, very similar to what we do with z-scores when we do those problems, convert this, okay, using a little bit of z-score magic to the standard normal distribution. All right, standard normal distribution. All right, the standard normal distribution has a mean of what? 0. And it has a variance and standard deviation of 1. If we can convert any old sampling distribution to a standard normal distribution, we can now use the cutoffs for the standard normal distribution to make our decision about whether or not we reject or retain the null hypothesis. All right. So if we have a two-tailed test, okay, here is our standard normal distribution. Kind of beautiful, not really. If this is our standard normal distribution and we have a two-tailed test, we only want to make an error, a type 1 error, 5% of the time. Okay, so we need to find out the location on the standard normal distribution here and here, that the probability of getting lower than this one particular score is our type 1 error rate divided by 2, and the probability of getting a score above this cutoff if the null hypothesis were true is also the type 1 error rate divided by 2, which in both of these situations would be 0.025. So we need to look up the spot in the z-table in the standard normal distribution in which the area above that score is a 0.025, and the area below this cutoff is 0.025 as well. So let's go and look at that. Okay. Give me 1 second here. Oh, that's cool. It still stays there. All right, here's our table. I'll try to move the table so that there we go, maybe. Let's zoom in. All right, what is the z-score that we find the value that 0.025% of people score above it? Ooh, it's highlighted. The number is 1.96. All right, and what is it on the lower side of the distribution? Well, we can take, we know that the normal distribution is symmetric about its mean. So we can say that the other value is just negative 1.96. All right, so let's go back to where we were. Okay, so in looking up on that z-table, I found out, or we found out rather, that positive 1.96, that's the value that if it's above that, we have 2.5% of people score above that. The value over here, since I know that this distribution is symmetric about its mean, is negative 1.96. All right, and it's always going to be positive 1.96 and negative 1.96 when we have a two-tailed test for a one sample z-test. So this is an important number to memorize here. Okay, so the cutoff, oops, there we go. The cutoff value, if we find a test statistic that's above positive 1.96 or below negative 1.96, we reject the null hypothesis. If it is in the middle, which it should be most of the time if the null hypothesis is true, we retain or we fail to reject the null hypothesis. This is what I want you to write for this problem. The next part that I'm going to show you, you don't have to write, but it makes things a little bit more clear, so that's why I'm going to include it. So if z that we're going to calculate is greater than positive 1.96, then we reject the null. Or if z is less than negative 1.96, we're going to reject the null. But if z is in between these, if it is negative 1 or positive 1 or 0.3, if it's between these 2 points, then we're going to fail to reject the null hypothesis. We're going to retain the null hypothesis. The null hypothesis is fairly likely, okay? Or that we don't have any evidence to support us rejecting the null hypothesis. It's still an adequate fit for our data. Okay, So all that's fine and dandy, but how do we actually calculate this statistic? Well, the formula for a one-sample z-test is going to look oddly familiar. Here it is. Now, these formulas are equivalent. They're exactly the same thing algebraically. The only difference that we have here is if we have the population mean, we could use this formula. If we have the population standard deviation, we can use this formula, or we can just alternate between the two of them. It doesn't really matter, but I just wanted to show you both versions of this. Let's look at this one, though, because it's going to show you something interesting here. This should look familiar. It's something minus something else over a standard deviation. Does it look familiar? It looks like the formula for calculating a z-score. The only difference here between this formula and calculating a z-score is we're subtracting a sample mean from a population mean instead of subtracting a raw score value from a mean. Okay, so that's slightly different. And the other difference is here in the bottom, in the denominator, instead of just having the standard deviation, we have it the standard deviation over the square root of n. All right. But theoretically, this is almost identical to a z-score. This thing right here, you might not think is a standard deviation, but it is, right? This is the standard error of the mean, which is the standard deviation of a sampling distribution. All right, so that's what we have here. That sampling distribution is going to look different depending on the number of subjects that we sampled. Okay, that's what's going on down here. And this, okay, what we have here is we're finding a sample mean and we're seeing how similar it is to the true population mean. Okay, that's what's going on right there. So let's do this math. So for Mac users, we had a sample mean of 15 minus the population mean of 20 all over, and I decided to do this formula, but I could have just as easily done something a little bit simpler, done this formula and had 6 over the square root of 25. All right, but the denominator in each case would be exactly equal. So we have -5 over 1.20, which gives us a z-value of -4.167. All right, so -4.167. Do we retain or do we reject the null hypothesis? Well, -4.167 is less than -1.96. So we're going to reject the null hypothesis, okay? And I'm going to put this right here, okay? I'm going to compare it to the cutoff. And what I might do if I wanted to is write, we reject the null hypothesis here, but I'm comparing it to my cutoff. We're going to infer that there's a true population mean difference between people that own a Mac and people that are just in the national average, okay? Population mean for creativity for Mac users is different than the national average. That is the conclusion that we are going to make. Now, here's a general thing that I want to mention to you guys. All right, when we look at all of these inferential statistics, all of them in this class are going to be a ratio of something in the numerator over something in the denominator. Okay. Every inferential statistic is going to be a ratio of evidence that supports the null hypothesis in the numerator, the top part of the fraction, and evidence in favor of the null, okay, in the denominator, the bottom part of the fraction, okay? So if there is more evidence in favor of an effect, there's a greater mean difference, what we're going to see is that the test statistic is going to be vastly different than 0. Okay, the test statistic is going to be very positive or the test statistic is going to be very negative. All right, if there's a lot of evidence in favor of the null, okay, there's a lot of random variation that's going on, a lot of sampling error that's going on, the numerator or the denominator, the bottom part of the fraction is going to shoot up. And the bigger this is going to be in relationship to evidence in favor of the alternative hypothesis, what that's going to do is it's going to shrink the test statistic. That z-value is going to get closer and closer to 0 because that denominator is going to be larger and larger. Another way of referring to this is maybe it is the magnitude of the mean difference. So is it a large mean difference? Is it a small mean difference? Over how much natural variation there is in whatever the dependent variable is. Okay, what is our sampling error? What is the natural amount of variability that there is in this type measure? Another way of looking at this comes from communication theory and communication science. All right, it's the amount of signal over the amount of noise. All right, psychology is very influenced by communication theory, especially cognitive psychology. All right, think about, if you would, you are in a submarine and you have a sonar, and it's your job to make sure that there's no enemy vessels coming around. So you've got your sonar, and the way that sonar works is there's all these kind of bleeps and bloops that are going around. There's all of this noise, but it's your job to tell if the bleep and the bloop is so significant, it's so large that it actually is an enemy vessel. All right, so you have to tell the difference between the signal and the natural amount of noise that is going on. And that's what we're doing here with null hypothesis significance testing. Okay, obviously these sample means are going to fluctuate a little bit just due to natural variability, just due to sampling error. But is the difference so large that it is very unlikely that we found that difference just due to chance, just due to natural variation? That's what this process is all about. So moving on, how do we do step 4? How do we state the conclusion? Well, there's a number of things that I want you to include in step 4, and I'm going to write them all out now, and then we're going to see them in practice here in a second. The first thing that we're going to want to include, okay, is what we do with the null hypothesis. We reject the null hypothesis, or we retain or fail to reject the null hypothesis. Remember, we never accept it. All right, we're never testing the null hypothesis to see if it's true in null hypothesis significance testing. We're using it, we're using the null hypothesis to give us some information about whether or not there is an effect. So we never accept the null hypothesis. All right, we're going to write out in English what is the alternative hypothesis if we're rejecting the null, or what is the null hypothesis if we are retaining the null. So we're going to write out in English what those hypotheses were. All right, we're going to write out what conditions, if we've got an experimental and control condition. We're going to write out the samples. Okay, are we comparing a sample to a population? Okay, are we comparing MAC users to the national average? Are we comparing the experimental condition to the control condition? Are we comparing people that own a dog to the national average? We need to write out what these population means actually are. Okay. We also need to write out the dependent variable. So we need to include something about these being creativity scores. We can't just say, well, the scores are significantly different. We need to mention what exactly those scores are. We need to include the descriptive statistics, so the means and standard deviations if we have them. And then we're going to include all of the statistical information. The relevant statistical information that we are going to have, what is the Z score, the Z value that we ended up calculating. We calculated that a slide or two ago. We're going to make sure that we include that. We're also going to include the p-value. Remember what the p-value is. It's the probability of obtaining this result or a more extreme result just due to chance. Okay. We can't calculate the p-value. We get SPSS to do that because calculating the p-value is going to be quite onerous, quite cumbersome, require a lot of math. But we do know that the p-value, if we reject the null hypothesis, is less than 0.05. The p-value would be exactly 0.05 if our Z was at 1.96, okay? Because that's the value that we decided to select, our cutoff value, where our type 1 error rate is 0.05. the probability that we found this result if the null hypothesis were actually true. Okay, so we know that the p-value, if we reject the null hypothesis, is less than 0.05. We know that the p-value is greater than 0.05 if we retain the null hypothesis. So when we do these calculations by hand, we'll put p is less than 0.05 when we reject the null hypothesis, because we know that it has to be, and that p is greater than 0.05 if we are retaining the null hypothesis. If SPSS is used, we don't need to say less than 0.05 or greater than 0.05. We just put the actual p-value there because SPSS can calculate it. All right, so that's what we are going to do. For some statistics, there are things called degrees of freedom, and we want to make sure that we include those as well, but you don't need them for a z-test. In the next module, we'll talk about what effect size is, and we want to make sure that we include effect sizes at the end of our step 4 as well, but we haven't talked about that yet, so we will ignore that for right now. Okay, so let's talk about what we want to do for step 4. So we say we reject the null hypothesis. Okay, that's part 1, in favor of the alternative. And we want to explain the alternative hypothesis in English. That MAC users' population mean creativity scores is different than the national average. All right, so I'm explaining what the alternative hypothesis is. In fact, if we were to go way back here, okay, this is the population mean of MAC users' creativity scores does not equal the population mean of the national average of creativity scores. I have written out essentially what's there, just instead of in mathematical notation, I wrote it out in English. Okay, let's go back. All right. I have included the fact that one of the means is from MAC users, the other mean is the national average. I've included the dependent measure, which are creativity scores. I've included the descriptive statistics, so I've got the mean of the sample, and I've got the standard deviation of the sample. Even though we didn't use the standard deviation of the sample in the problem, I still made sure that I included it. I've got the information here, the descriptives for the population mean and the population standard deviation. And then I have my z-value that I calculated and the fact that I know that it is less than 0.05. Okay, the p-value. A couple of things here in writing this all down. Notice that when I'm writing this up in APA format, all of my statistical letters here are italicized. Okay, that is the appropriate way to do things. I get, when I'm teaching this class, I sometimes will not italicize things because it's on the board and it's hard for me to do that. But when we're writing this up, if we're typing this up, we need to make sure that it's italicized. It's not like I'm going to take off points for that. I'm just letting you know what is appropriate APA style. Another thing, notice in this one, if I'm talking about population mean, okay, this population mean is different than this other one. I'm not talking about a statistical difference. I'm not talking about a statistically significant difference. If I'm referring to population means, I just care about if there is a difference at all. There's another way of writing step 4. I could write it in terms of the sample means. Okay, we reject the null hypothesis in favor of the alternative that the sample mean for MAC users. Notice instead of population mean, I said sample mean. And I don't care if the sample mean is different than the national average. No duh, I can look at the sample mean and tell it that it's different than the national average. Okay, that's not what I care. What I care about if the sample mean is so different from the population mean that I infer that there is a true difference at the population level. So if I'm referring to sample means, I want to talk about a statistically significant difference. So in this case, I'm going to say that the sample mean for MAC users' creativity scores is significantly different than the national average. Okay. If the null hypothesis were true, I would say is not significantly different than the national average. Or I would say is non-significantly different. I would never say insignificant. Insignificant implies that your results are useless. Okay. That your research study is not good, and that's not what we want to apply. Okay, a lot of people get tripped up about the term significant here in statistical significance. So let's talk a little bit about that. Statistical significance. This is referring to the difference between our sample mean and our population mean, or maybe between two sample means if we're doing an independent samples or paired samples t-test. The difference is so large that it leads us to reject the null hypothesis. This is a finding that is statistically significant. Now, don't confuse, where do I have here? Don't confuse statistical significance for importance, okay? Even though it says significant, and that typically implies importance, don't get confused by this. There might be a difference so itty-bitty small that we say that there's a statistically significant difference, but practically there's really no difference, okay? Maybe it's the case that there is no difference between these two population means, and we say that the result is not statistically significant, but that's a very important finding sometimes, okay? Just going for some of my research, the finding that training or cognitive training does not work is a very significant finding. It's not statistically significant in that we didn't find an effect that training on a dumb memory task ends up improving your intelligence. That's not what we found, but that doesn't mean that the result is insignificant. So we want to use the term significant or non-significant. We never want to use the term insignificant because that implies that our results are not useful. And in many situations, our results are still useful. All right. So sample means can be both significantly different, but population means are only different. So we can say that sample means are significantly different from one another, but population means are not significantly different from one another. We don't say that. Okay, we just care about is there a difference, point blank, period, at the population level. All right. It's going to take some while to wrap your mind around what's going on here. I will stop the video right now. We'll do some more examples of one sample z-test, and then we'll talk about assumptions of null hypothesis significance testing. Thank you guys for your attention, and have a wonderful day.